Right, so we're going to have a little bit of a look at the Doppler effect. And Doppler effect is quite an interesting one. What we have is this situation here. If I've got a person here standing there shouting out hello or some such, you could basically see the sound waves emanate out from them, and well, obviously nice beautiful circles, not necessarily like the ones I'm drawing, but you get the idea. Well, the beautiful circles coming out from our observer, or from our person who's making noise. He's actually an emitter, if you will. So he's our emitter, giving out this sound. And you see it's travelling in all directions at the same velocity, the same speed. And one of the questions that we start to ask is, what happens if our observer isn't standing still? What if they're moving? What if our observer, in this case, is on the back of a car, shouting out, hello? Well, what you find happening, of course, you've got the sound moving in this direction as they're emitting it, but the car is also moving in this direction. So the sound behind gets farther away faster, but the sound in front doesn't get as far away as it would normally, so it actually gets bunched up like that. There we go. And this actually has some interesting end effects. So a person on this side of the car, what they're going to hear is they're going to hear sound waves that are very far apart. There we go. The wavelength is very long, which means the frequency has gone down. A person on this side of the car, because the waves are still travelling away from the car, they're just getting bunched together. They're going to hear waves which are much closer together, or at least reasonably close together, which means the frequency that they're hearing goes up. Well, why does the frequency change? Why does the wavelength change? Because the speed is constant. You can't have one thing being affected and not the other. You can see here the wavelength is changing. The wavelength is getting much smaller on this side. If the wavelength on this side gets smaller, then the frequency gets bigger, because our speed, v, is frequency times wavelength. And the same on this side. If our wavelength gets larger, the frequency gets smaller. Alright. So this is quite interesting. This actually is quite well behaved. We can work with this. This actually leads us to an equation, which is, something which will tell us how much the frequency has changed by. So here we go. We've got our frequency. The one we're going to measure will be equal to V plus or minus V of the observer divided by V plus or minus V of the source. Okay. Now what does this mean? Well, you know what? This is for a moving observer. Why? Well, because here, if I've got an observer moving and the source is stationary, what's going to happen is they're going to hear these wavelengths as if they're much closer together, if they're travelling towards the source. If the person is travelling away from the source, they'll hear the waves much further apart. So there we go. We can see that that's actually got an effect. What the observer is doing affects the result. Okay, so where are we? Here we go. This is if the observer is moving towards the source, and this is if they're moving away. And if they're not moving, then this second section is just zero. It doesn't exist. Okay, the next bit down the bottom is when the source is moving. Alright, so if the source is moving Put that in so it's nice and clear. There we go. There's a negative there. That's it. Oh dear me. Try to get it so it looks clear, and I'm making a hash of it, aren't I? Alright, there we go. If the observer is moving towards the source, oh sorry, if the source is moving towards the observer at this velocity, then we use a negative down here. And if the source is moving away from the observer, there we go. So what do we have? We've got a moving source down the bottom and a moving observer up the top. Looks scary, but it's not. Let's have a little bit of a glance at it. See if we can't use it. So here we go. A speaker, a loudspeaker, is moving. We'll give it a speed. Yeah. With speed 30 meters per second towards an observer. It has a frequency. It emits a frequency of, let's say, 300 hertz. What frequency does the observer hear? Well, let's have a look at that. Well, frequency is going to be equal to 300 hertz multiplied by this kind of whole thing in here. So we've got up top, we've got V of the velocity of sound. In fact, actually I need to put that in the question, don't I? Take V of sound to be equal to 343 meters per second. There we go. That's fine. So, what does that give me? All of these V's get replaced with 343. So this is 343 on top, and on bottom I've got 343. Now, is my observer moving? Well, let's see. I've got a loudspeaker that's moving towards an observer. The observer here isn't moving. So, plus or minus is nothing. So 0 up top. Now, we've got a source moving towards our observer. So the source is moving towards. There we go. That's it. 343 minus 30 meters per second. There we go. Okay. So my equation becomes 300 hertz multiplied by 343 divided by 313. Let's put it into the calculator and see what it gives us. $329 hertz. So the frequency has actually changed. The frequency that the observer will hear has changed. Well, what if the speaker is moving away? Moving away. With speed, say 50 meters per second. Stationary observer, let's put frequency is 500 hertz and velocity of sound is 343 meters per second. There we go. Okay, so we get an interesting question there. Let's see what happens. Well, the frequency we're going to hear will be equal to 500 hertz. Lots of 343 divided by 343. We've got a moving source here. A moving source means because it's moving away, it's plus on the bottom, so plus 50. It's going to give me 500 multiplied by 343 divided by 393. There we go. Let's put that in our calculator and see what it gives us. 343 divided by 393 equals 0.7 times 500. There we are, 436 Hertz. So quite an interesting little setup there. All right. Last one. How about if our observer is moving? Observer moving away. Say at 40 meters per second. Loudspeaker has a frequency of 300 Hertz. And there we go. Let's see. So we're moving. The observer is moving away at 40 meters per second. The loudspeaker is giving us this thing. We'll take this velocity of sound, the speed of sound, to be equal to 343 meters per second. Let's put that into our equation and see what it gives us. Here we go. We start off here. The sound we're going to hear is going to be equal to the frequency that we start with, 300 Hertz, multiplied by, we've got the sound in this case, the observer in this case is moving away. So we've got a moving observer, the observer is moving away. It's going to be speed of 343 minus 40, divided by the speed of sound, 343, and the source isn't moving, so this is where we stop. Well, there. So that gives us 300 Hertz multiplied by 303 divided by 343, which will give us a value of 265 Hertz. And there we go. All right. So hopefully that's quite useful.